Tonight, we're going to follow a journey that no human being will ever witness from beginning to end. Not because it's too far away, but because it lasts so long that every civilization alive today will disappear before even the first chapter is complete. Imagine building a machine that continues moving long after every city on Earth has turned to dust, long after every language has been forgotten, long after our species itself has vanished. That machine already exists. Right now, more than 24 billion kilometers from Earth, a spacecraft no larger than a small car is quietly drifting through the darkness between the stars. It has no destination, no rescue mission is coming, no one will ever bring it home. Its name is Voyager 1. When Voyager 1 launched in 1977, its original mission was surprisingly simple. It was built to explore Jupiter and Saturn, collect scientific data, and send breathtaking images back to Earth. Engineers expected the mission to last only a few years. No one imagined that nearly half a century later, it would still be traveling farther into deep space than any human-made object in history. But the most extraordinary part of Voyager's story isn't what it has already accomplished. It's what happens next. Because Voyager's greatest journey doesn't begin near Jupiter, or beyond Saturn, or even after leaving the solar system. Its real journey begins after every person alive today is gone. Every second, Voyager 1 moves deeper into interstellar space at nearly 17 kilometers per second. That sounds unimaginably fast, yet on the scale of the universe, it is almost motionless. If the distance between Earth and the nearest star were reduced to the length of a football field, Voyager would still be crawling forward only a few millimeters each second. Space is simply too vast for human intuition. And that's what makes this story so extraordinary. Most documentaries focus on places humans hope to visit one day: Mars, Europa, Alpha Centauri. But tonight, we're following something that will continue traveling for thousands, millions, even billions of years after humanity's own future becomes uncertain. Where does a spacecraft go when time itself stops making sense? Will it ever reach another star? Could it survive longer than the sun? Will another civilization ever discover it drifting through the darkness? Or will it spend eternity wandering an increasingly empty universe until even the stars themselves begin to disappear? These aren't questions from science fiction. Modern astronomy allows us to make surprisingly realistic predictions about Voyager's future. We know how the Milky Way rotates. We can estimate how stars move through our galaxy. We understand how the sun will evolve, how galaxies will collide, and even how the universe itself is expected to change over unimaginable spans of time. For the first time in history, we can attempt something extraordinary. We can follow the future of a human-made object not for decades, not for centuries, but for 1 trillion years. And the deeper we travel into that future, the stranger reality becomes. The solar system will transform beyond recognition. Entire constellations will vanish. The night sky itself will become unrecognizable. Galaxies will collide, stars will die, and the cosmos will slowly drift toward a future unlike anything our ancestors could have imagined. Through it all, Voyager 1 may still be there. Silent, dark, still moving, still carrying a golden record filled with the sounds, music, and greetings of a civilization that may no longer exist. By the end of this documentary, we'll trace Voyager's journey farther than almost any human story has ever dared to go. We'll explore not only where it will be, but what will happen to it as the universe ages around it. Because the most fascinating question isn't whether Voyager will survive. It's whether the universe around Voyager will. And to understand that journey, we have to return to a warm summer morning in 1977. When humanity unknowingly launched the longest voyage it would ever begin. On September 5, 1977, Voyager 1 lifted off from Cape Canaveral carrying a mission that seemed remarkably straightforward. It wasn't built to cross the galaxy. It wasn't designed to search for alien civilizations or survive for geological ages. Its purpose was far more modest: visit the giant planets, send home as much scientific data as possible, and then eventually fall silent. At the time, no one imagined that this small spacecraft would become humanity's most distant ambassador. Voyager's first destination was Jupiter. When it arrived in 1979, it transformed our understanding of the largest planet in the solar system. Its cameras revealed volcanic eruptions on Io unlike anything ever seen beyond Earth. It photographed immense storms, discovered faint planetary rings, and captured details that scientists had only dreamed of observing. For millions of people watching from Earth, it felt as though humanity had stepped into an entirely new era of exploration. Then came Saturn. In 1980, Voyager 1 delivered another scientific revolution. It revealed astonishing complexity within Saturn's rings and provided humanity's first close look at Titan, the mysterious moon wrapped in a thick orange atmosphere. Those observations alone justified the entire mission. By every measure available at the time, Voyager 1 had already exceeded expectations. Most spacecraft would have ended their story there. Voyager didn't. After Saturn, there were no more scheduled planetary encounters, no destination waiting farther ahead, no dramatic flyby planned decades into the future. The spacecraft simply continued moving outward, carrying the momentum it had gained during its encounters with the giant planets. Every second, it drifted farther from the sun and farther from the world that had created it. Without realizing it, humanity had launched something very unusual. Not just a probe, a message. Bolted to Voyager's side is one of the most extraordinary objects ever sent into space, the Golden Record. Covered in gold and carefully protected inside an aluminum case, it contains music from different cultures, greetings spoken in dozens of languages, sounds of nature, scientific information, and images of life on Earth. It was never intended as a practical communication device. Instead, it was a time capsule, a snapshot of a civilization hoping that, somewhere in the unimaginably distant future, someone, or something, might discover it. The odds of that happening are almost impossibly small. Interstellar space is so unimaginably vast that Voyager could travel for millions of years without coming remotely close to another planetary system. Even if another civilization exists somewhere in our galaxy, the chances of this tiny spacecraft crossing its path are almost zero. And yet the record remains. Not because scientists expected it to be found, but because it says something profound about humanity itself. We looked into an ocean billions of times larger than anything our species had ever crossed, and instead of remaining silent, we left behind a greeting. As the decades passed, Voyager continued transmitting data back to Earth. The signal grew weaker every year, taking longer and longer to arrive. Today, every message sent from Voyager travels for more than 23 hours before reaching our planet. The spacecraft is now so distant that radio signals move across billions of kilometers before a faint whisper is finally detected by NASA's Deep Space Network. Yet even at that extraordinary distance, Voyager kept going. Then, in 2012, it crossed a boundary that humanity had pursued for generations. It entered interstellar space. For the first time in history, a human-made object had traveled beyond the protective bubble created by our sun. Voyager was no longer exploring the solar system. It had begun exploring the space between the stars. That achievement sounded like the end of a journey. In reality, it was only the beginning. Because despite traveling for nearly half a century, despite becoming the most distant object humanity has ever built, Voyager 1 hasn't even completed 1% of the journey to the nearest star. If that sounds impossible, it's because the universe operates on scales that our brains were never designed to understand. And before we can follow Voyager through millions, billions, and eventually trillions of years, we first have to confront the greatest obstacle ever faced by any spacecraft: the true size of deep space. Voyager 1 has now traveled farther from Earth than any object in human history. It has crossed the boundary of the solar system and entered the darkness between the stars. By any human standard, it has traveled an unimaginable distance. And yet, in cosmic terms, it has barely left home. This is where our intuition begins to fail. Human beings evolved to understand distances measured in meters, kilometers, and perhaps the occasional journey across an ocean. Even the size of Earth is difficult for our brains to truly visualize. Space, however, operates on a completely different scale, one so vast that the numbers themselves stop carrying meaning. To appreciate Voyager's journey, imagine shrinking the entire solar system. Suppose the Sun were the size of a basketball sitting at the center of a large city. Earth would become a tiny grain of sand orbiting several dozen meters away. Jupiter would be a marble hundreds of meters farther out. Neptune, the most distant major planet, would lie nearly a kilometer from the basketball. Now imagine Voyager 1. After traveling for almost 50 years at roughly 17 kilometers every second, it has finally moved beyond the edge of that miniature solar system. It feels like an incredible achievement. Because it is. But the nearest star in this model wouldn't be another kilometer away. It wouldn't even be in the same city. The nearest star would be thousands of kilometers away on another continent. That is the true scale of interstellar space. The emptiness between stars is so enormous that even our fastest spacecraft appear almost motionless against it. Every second Voyager moves forward. Every hour it travels more than 60,000 kilometers. Every year it covers hundreds of millions of kilometers. Yet compared to the distances separating one star from another, that progress is almost invisible. This is why so many science fiction stories unintentionally mislead us. Movies often show spacecraft jumping from one star system to another as though crossing countries on a map. In reality, the stars are not neighbors. They are isolated islands separated by oceans so vast that light itself requires years to cross them. Light is the fastest thing known to exist. Nothing carrying information can travel faster. Every second, light races through space at nearly 300,000 kilometers. In just over 1 second, it could circle Earth more than 7 times. Even at that extraordinary speed, sunlight still takes about 8 minutes to reach our planet. The light leaving the Sun today won't reach Jupiter for more than 40 minutes. To Neptune, it travels for over 4 hours. And to the nearest star beyond our solar system, it travels for more than 4 years. Now compare that with Voyager. Unlike light, Voyager isn't moving at 300,000 kilometers every second. It's moving at about 17. The difference is almost impossible to comprehend. If a beam of light and Voyager 1 left the solar system together, the light would arrive at Alpha Centauri long before Voyager had covered even a tiny fraction of the journey. In fact, at its current speed, Voyager would need tens of thousands of years just to reach the region around the nearest star. And that's assuming the stars themselves stayed perfectly still. They don't. Every star in the Milky Way is moving. Our Sun orbits the center of the galaxy at hundreds of kilometers every second. Neighboring stars follow their own paths. Entire stellar systems drift through space like ships crossing an endless ocean. That means Voyager isn't aiming at a fixed destination. Its target is constantly moving. The galaxy itself is changing, while Voyager slowly makes its way through it. Suddenly, the mission begins to look very different. This is no longer a journey between planets. It's a journey across a living galaxy, one where the map is constantly changing. And that realization raises an extraordinary question. If the stars themselves refuse to stay still, how can we predict where Voyager will be not just thousands of years from now, but 1 trillion years into the future? If the nearest star is so unimaginably far away, an obvious question follows. Why not simply build a faster spacecraft? After all, human history is filled with technologies that seemed impossibly slow until someone invented something better. We replaced horses with trains, trains with airplanes, and airplanes with rockets. Surely the next step is simply a faster rocket, one capable of crossing interstellar space within a human lifetime. Unfortunately, the universe doesn't make that easy. The problem isn't a lack of engineering, it's the laws of physics themselves. Every spacecraft ever launched has had to carry energy, fuel, and mass. The faster you want to travel, the more energy you need. But adding more fuel also increases the spacecraft's mass, which means you need even more fuel to accelerate it. It's a cycle that quickly becomes impossible. Long before engineers reach the speeds imagined in science fiction, the mathematics begins working against them. Even the most ambitious propulsion concepts scientists are studying today struggle against this reality. Nuclear fusion engines, antimatter propulsion, giant laser sails, and other advanced ideas could one day make interstellar travel more practical, but none of them eliminate the enormous distances involved. They only reduce a journey that would take tens of thousands of years into one that might still last decades or centuries. And during every second of that journey, deep space continues to fight back. Unlike the dramatic explosions shown in movies, space is terrifying because almost nothing happens. There is no atmosphere, no sound, no nearby planets, no rescue stations waiting over the horizon. A starship crossing interstellar space would spend years looking out at almost complete darkness, surrounded by an emptiness so vast that the nearest sun would appear as nothing more than another bright point among countless others. That isolation creates a psychological illusion. It makes deep space seem peaceful. It isn't. Interstellar space is filled with invisible dangers that never stop. High-energy particles, known as cosmic rays, constantly race through the galaxy at nearly the speed of light. Produced by exploding stars, supernova remnants, and some of the most violent events in the universe, these particles carry enormous amounts of energy. On Earth, we're largely protected by our atmosphere and the magnetic field surrounding our planet. A spacecraft traveling between the stars would have no such natural shield. Over years or decades, that radiation would slowly damage electronics, weaken materials, and increase serious health risks for any human crew. Every system on board would have to survive an environment unlike anything experienced within Earth's protective bubble. The farther a spacecraft traveled from the sun, the more completely it would depend on its own engineering to remain alive. Then there is another threat, one that seems almost impossible until you consider the speeds involved. Dust. Interstellar space isn't completely empty. Tiny grains of rock and ice drift silently between the stars. Most are smaller than grains of sand, and under ordinary circumstances, they would seem harmless. But when a spacecraft is moving at a significant fraction of the speed required for interstellar travel, even a microscopic particle can strike with the energy of an explosive projectile. A single impact could punch through shielding, destroy sensitive instruments, or trigger catastrophic failures if critical systems were exposed. The faster humanity learns to travel, the more dangerous the smallest particles become. Suddenly, deep space no longer looks like an empty highway waiting to be crossed. It begins to resemble an endless ocean filled with hazards that are almost impossible to see until it's too late. Every kilometer brings another chance encounter. Every year places more stress on machines that cannot be repaired from Earth. Every decade increases the odds that something, no matter how small, will eventually go wrong. And that's exactly what makes Voyager 1 so remarkable. Unlike the giant starships imagined in science fiction, Voyager has survived this hostile environment for nearly half a century with technology designed in the early 1970s. It has endured freezing temperatures, relentless radiation, and unimaginable isolation, while continuing to whisper faint signals across billions of kilometers back to Earth. In many ways, it has already achieved something extraordinary. But Voyager possesses one enormous advantage that a future interstellar starship never will. It doesn't have to keep anyone alive. The moment human beings step aboard a spacecraft bound for another star, the challenge changes completely. Survival is no longer measured by whether the spacecraft continues moving. It's measured by whether the people inside can endure the journey. And that transforms interstellar travel from an engineering problem into one of the greatest survival challenges humanity has ever faced. By now, Voyager's journey has forced us to confront an uncomfortable reality. The universe is far larger than our intuition can comprehend. Even after nearly 50 years of continuous flight, the most distant spacecraft ever built has barely begun the journey to another star. That realization naturally leads to an obvious question. If distance is the problem, why don't we simply build a much faster spacecraft? At first, the answer seems simple. Human history is built on faster transportation. We replaced walking with horses, horses with trains, trains with airplanes, and airplanes with rockets. Every generation solved the limitations of the one before it. From that perspective, interstellar travel appears to be just another engineering challenge waiting for a better engine. Many people assume that once technology advances far enough, crossing the galaxy will become as routine as crossing an ocean. Unfortunately, the universe doesn't negotiate with optimism. Every spacecraft ever launched has obeyed the same unforgiving laws of physics. To move faster, you need more energy. To carry more energy, you need more fuel. But the moment you add more fuel, the spacecraft becomes heavier, requiring even more energy just to accelerate the extra mass you've added. That additional fuel also has weight, demanding even more fuel to move it. Engineers call this the tyranny of the rocket equation, and it has quietly shaped every mission humanity has ever attempted. Imagine trying to climb a mountain while carrying enough food for the entire journey on your back. The extra food makes you heavier, forcing you to consume more energy. To support that extra effort, you need even more food, making your backpack heavier still. Eventually, most of what you're carrying exists only to support the weight of everything else you're carrying. Rockets face exactly the same problem. Beyond a certain point, adding fuel becomes less effective because so much of it is spent accelerating itself instead of the spacecraft. This is why leaving Earth is so incredibly difficult. A rocket standing on the launch pad is mostly fuel. The payload, the scientific instruments, the astronauts, or the spacecraft itself often represents only a tiny fraction of the vehicle's total mass. Even before humanity dreams of reaching another star, we've already spent decades fighting gravity simply to escape our own planet. But escaping Earth is only the beginning. Reaching another star demands speeds unlike anything humanity has ever achieved. Voyager 1 travels at about 17 kilometers every second. That sounds astonishing until it's compared with the speed of light, which races through space at nearly 300,000 kilometers every second. Voyager is moving at less than 1/100% of light speed. At that pace, the nearest stars remain tens of thousands of years away. So why not accelerate to a significant fraction of the speed of light? Because every increase in speed makes the challenge dramatically more difficult. The energy required doesn't grow steadily. It grows rapidly until the numbers become almost unimaginable. A spacecraft carrying hundreds of people, shielding against radiation, life support systems, food, water, and decades of supplies would require an amount of energy that rivals the output of civilizations rather than individual machines. This is why scientists have explored ideas that sound almost like science fiction. Nuclear fusion engines could release far more energy than chemical rockets. Antimatter propulsion promises extraordinary efficiency if it can ever be controlled safely. Massive laser arrays might push ultralight spacecraft using beams of light instead of onboard fuel. These concepts are grounded in real physics, and researchers continue studying them today. Yet none of them perform magic. They don't erase the distance between the stars. They simply reduce a journey measured in tens of thousands of years into one measured in decades or centuries. The destination moves closer, but it never becomes easy. And then another realization begins to emerge. Even if humanity solves propulsion, even if we build an engine powerful enough to reach another star within a single lifetime, that engine solves only one problem. The spacecraft still has to survive the journey. Because deep space isn't an empty highway waiting to be crossed. It's an environment that quietly attacks everything passing through it. Radiation never stops. Tiny particles become high-speed projectiles. Machines slowly wear down. Every system aboard the spacecraft must continue functioning year after year without failure, repair, or rescue. The faster we travel, the more dangerous those invisible threats become. Ironically, the greatest obstacle to interstellar travel may not be building a faster ship. It may be surviving what that speed creates. And the first enemy waiting beyond the solar system is completely invisible. If building a faster engine isn't enough, then the next question becomes unavoidable. What exactly is waiting for a starship once it leaves the safety of our solar system? From the windows of a spacecraft, the answer would appear to be almost nothing. No explosions, no monsters drifting through the darkness, no dramatic asteroid fields stretching across space. Hollywood has trained us to expect danger that we can see. The real universe is far more deceptive. Deep space looks calm because its greatest threats are invisible. Imagine leaving Earth's atmosphere forever. Within hours, our planet becomes a bright blue dot behind you. Days later, the sun begins looking less like the overwhelming object that dominates our sky, and more like an unusually bright star. As months become years, every familiar landmark disappears. Eventually, there is nothing outside your spacecraft except darkness scattered with distant points of light. It would be easy to believe you've entered the safest place imaginable. In reality, you've entered one of the most hostile environments in the universe. The first enemy is radiation. Here on Earth, life exists beneath two extraordinary layers of protection. Our atmosphere absorbs enormous amounts of harmful radiation before it can reach the surface, while Earth's magnetic field deflects many of the charged particles streaming through space. These invisible shields have protected life for billions of years. Without them, complex organisms like ourselves might never have evolved. The moment a spacecraft leaves that protective bubble, those natural defenses disappear. Across the Milky Way, exploding stars continuously launch high-energy particles in every direction. These cosmic rays travel through interstellar space at astonishing speeds, carrying enough energy to penetrate metals, damage electronics, and even alter the DNA inside living cells. Unlike a storm that eventually passes, this bombardment never truly ends. Every hour spent in deep space adds a little more damage than the hour before. For robotic spacecraft like Voyager 1, that damage accumulates slowly over decades. Engineers designed its systems with remarkable durability, yet even Voyager has gradually lost instruments and experienced failures as its electronics aged in one of the harshest environments imaginable. Despite its incredible success, time is quietly winning. Now imagine replacing a robotic probe with a crew of human beings. Every astronaut aboard would face a threat that cannot be seen, heard, or felt in the moment it strikes. A single energetic particle can pass directly through the human body, leaving microscopic damage behind. One event is unlikely to be catastrophic, but over years or perhaps generations, those tiny injuries begin to accumulate. The risk of cancer rises. Sensitive tissues become increasingly vulnerable. Even the brain may experience subtle changes that scientists are still trying to understand. Protecting a crew sounds simple, just build thicker walls. But thicker walls mean more mass. More mass requires more fuel. More fuel demands a larger spacecraft. And suddenly, we're trapped by the same laws of physics we encountered earlier. Every solution creates another problem. Engineers can design advanced shielding using water, specialized materials, or magnetic fields that imitate Earth's own protection. These ideas show real promise, but none provide perfect safety. Every kilogram of shielding must be accelerated across trillions of kilometers, forcing difficult compromises between protection, speed, and the resources needed to complete the mission. This is the reality of interstellar travel. It's not a battle against one overwhelming obstacle. It's thousands of interconnected problems, each making the others more difficult to solve. And radiation is only the beginning. Because while invisible particles quietly pass through your spacecraft every second, another danger is waiting in the darkness ahead. It's far smaller than a grain of sand. You would never see it approaching. There would be no warning alarm, no flashing lights, and no time to react. Yet at interstellar speeds, that tiny particle could carry the destructive energy of an explosive weapon. In deep space, even dust can become deadly. And as humanity dreams of building the first true starship, those microscopic grains may prove to be just as dangerous as the unimaginable distances between the stars. By the time Voyager 1 entered interstellar space, it had already survived countless dangers. It had endured the violence of launch, the intense radiation belts surrounding Jupiter, the freezing darkness beyond Saturn, and decades of relentless exposure to the vacuum of space. Yet the greatest threat wasn't waiting near a planet or hidden inside an asteroid field. It was already there, surrounding the spacecraft every second of its journey. Voyager couldn't see it. It couldn't avoid it, and neither could any future starship. This is one of the strangest truths about deep space. The farther you travel from Earth, the more peaceful the universe appears. There are no roaring storms, no crashing waves, and no sound at all. Look out of a spacecraft window, and the darkness seems perfectly calm, but appearances can be dangerously misleading. Interstellar space is filled with particles moving at extraordinary speeds, each carrying enough energy to damage electronics, weaken materials, and slowly erode the systems keeping a spacecraft alive. The silence of deep space hides an invisible storm that never ends. These particles are known as cosmic rays, and despite their name, they are not rays of light. Most are tiny atomic particles, mainly protons and heavier atomic nuclei, that have been accelerated to incredible speeds by some of the most violent events in the universe. When a massive star explodes as a supernova, it releases an enormous shockwave that can fling particles across the galaxy at speeds approaching the speed of light. Other cosmic rays may originate near neutron stars or the supermassive black holes lurking at the centers of galaxies. By the time they reach a spacecraft, they've often been traveling through the Milky Way for millions of years. On Earth, we rarely think about them because our planet quietly protects us. The atmosphere above our heads absorbs most of this radiation before it reaches the surface, while Earth's magnetic field deflects many charged particles away from the planet altogether. These invisible shields have protected life for billions of years. Without them, the history of life on Earth might have unfolded very differently. A spacecraft traveling between the stars has no such luxury. The moment it leaves the protective influence of the Sun and Earth's magnetic field, it enters an environment where these high-energy particles become an unavoidable part of everyday existence. They pass through metal, they strike computer systems, they slowly alter the microscopic structure of materials. Most impacts cause only tiny amounts of damage, but interstellar travel is measured in decades, centuries, and perhaps even generations. Over those immense spans of time, tiny damage stops being tiny. This is exactly the kind of challenge Voyager was never designed to face for so long. Engineers expected the spacecraft to operate for only a handful of years. Instead, it has spent nearly half a century enduring a continuous bombardment from one of the harshest environments in the solar system and beyond. The fact that many of its systems still function today is a remarkable achievement of engineering. But even Voyager has gradually lost instruments, experienced failures, and required ingenious solutions from engineers on Earth to keep transmitting data across billions of kilometers. Now imagine replacing Voyager with a starship carrying hundreds of people. Unlike electronics, human cells constantly divide, repair themselves, and store genetic information. High-energy radiation can damage that DNA one particle at a time. Most damage is repaired naturally, but not all of it. Over years of continuous exposure, the risks begin to accumulate. Scientists worry not only about increased cancer risks, but also about possible effects on the nervous system, vision, and long-term brain function. A crew might never notice the exact moment radiation harms them. The danger is silent, invisible, and relentlessly patient. This is what makes cosmic radiation so terrifying. It doesn't attack like an explosion. It doesn't announce its arrival with alarms or flashing lights. Instead, it slowly chips away at both machines and people, one invisible impact after another, while the spacecraft continues drifting through what appears to be perfect emptiness. And yet, astonishingly, radiation is not the danger that keeps spacecraft engineers awake at night. Because out there, hidden in the darkness between the stars, something far smaller than a grain of sand may be even more destructive. At the speeds required for interstellar travel, that tiny particle becomes a weapon powerful enough to tear through metal itself. To understand why, we first have to confront one of the most counterintuitive ideas in all of physics. In deep space, the smallest objects can become the deadliest. At first, the idea sounds almost ridiculous. After everything we've discussed, the unimaginable distances between the stars, the enormous energy required to reach them, and the invisible radiation constantly sweeping across the galaxy, how could something as insignificant as a tiny speck of dust possibly become one of the greatest dangers to a starship? The answer lies in a simple fact that governs the entire universe. Energy doesn't depend only on size, it also depends on speed. The faster an object moves, the more destructive even the smallest collision becomes. Here on Earth, a grain of sand bouncing off your hand is barely noticeable, but imagine that same grain traveling tens of thousands of kilometers every second. Suddenly, it is no longer dust. It has become a microscopic projectile, carrying enough energy to punch through metal, destroy delicate electronics, and send fragments flying through the interior of a spacecraft. This is one of the greatest paradoxes of interstellar travel. Building a faster ship doesn't just shorten the journey, it makes every collision exponentially more dangerous. A spacecraft moving at a significant fraction of the speed of light would never experience space as empty. Instead, every tiny particle floating between the stars would become a potential impact waiting to happen. The very speed needed to reach another star within a human lifetime transforms the emptiness of space into a shooting gallery. Fortunately, interstellar space is extraordinarily sparse. Compared with the dense environments around planets and young stars, the space between stellar systems contains remarkably little matter. But remarkably little is not the same as nothing. Over trillions upon trillions of kilometers, even an incredibly small number of dust particles adds up. A spacecraft crossing those immense distances cannot simply hope to avoid them forever. Eventually, probability begins to take over. Imagine driving through a light rainstorm. One raindrop striking your windshield means almost nothing. Drive long enough, however, and thousands of drops eventually hit the glass. Interstellar travel follows the same principle, except every collision occurs at speeds that no human vehicle has ever experienced. The challenge isn't avoiding one particle. The challenge is surviving millions of opportunities for something to go wrong. Engineers have spent decades thinking about this problem. Some proposed covering the front of a spacecraft with thick sacrificial shields designed to absorb repeated impacts. Others imagined enormous clouds of tiny particles released ahead of the spacecraft to collide with incoming dust before it reached the main vehicle. More advanced concepts involve electromagnetic fields or plasma barriers that could deflect certain particles away from the ship. None of these ideas are perfect, but together they reveal something important. Scientists aren't asking whether dust is dangerous. They're asking how humanity might survive it. Ironically, Voyager 1 rarely has to worry about this particular threat. Compared with the speeds proposed for future interstellar missions, Voyager is moving relatively slowly. At roughly 17 kilometers per second, collisions remain a concern, but they are nowhere near the catastrophic events predicted for spacecraft traveling at a significant fraction of the speed of light. In a strange twist of physics, Voyager's greatest limitation, its comparatively slow speed, is also one of the reasons it has survived for so long. A future starship won't be so fortunate. To make the journey practical, it must travel hundreds or even thousands of times faster than Voyager. Every increase in speed shortens the voyage, but every increase also magnifies the violence of even the tiniest impact. Engineers find themselves trapped in another cruel trade-off. The faster they make the spacecraft, the more dangerous the journey becomes. Slow ships may never reach another star within a human lifetime. Fast ships may struggle to survive getting there. This is why interstellar travel refuses to become a simple engineering problem. Every solution creates a new obstacle. More speed demands more energy. More energy requires new technology. New technology introduces new risks. Solving one challenge only reveals another waiting behind it. The deeper scientists explore the possibility of reaching another star, the more they discover that the universe has hidden layer after layer of unexpected difficulty. Yet perhaps the greatest challenge has nothing to do with engines, radiation, or microscopic dust. Even if humanity solved every engineering problem tomorrow, even if we built a spacecraft capable of surviving the journey, one question would still remain unanswered. Could the people inside survive a voyage that lasts longer than an entire human lifetime? Because keeping a machine alive is difficult, keeping a civilization alive inside that machine may be the hardest challenge of all. So far, every obstacle we've encountered has been physical. The distances between the stars are almost beyond comprehension. The rocket equation limits how fast we can travel. Radiation quietly damages both machines and people, while microscopic grains of dust become deadly at interstellar speeds. Each challenge seems enormous on its own, but together they point toward a far more unsettling conclusion. Reaching another star may not be humanity's greatest problem. Surviving the journey might be. For decades, science fiction has taught us that once we invent a powerful enough engine, interstellar travel will become inevitable. Build a faster spacecraft, point it toward another star, and wait until it arrives. It sounds perfectly reasonable until you remember one simple fact. Human beings are not spacecraft. Machines can operate for decades without food, sleep, or companionship. People cannot. This is where the dream of a real starship collides with biology. Imagine boarding a spacecraft that will never return to Earth. The moment the engines ignite, everyone on board understands the same reality. No rescue mission will ever reach them. No spare parts will be delivered. Every drop of water, every breath of oxygen, every meal, every medical supply, and every piece of equipment needed to stay alive must either travel with them or somehow be produced during the journey. The spacecraft doesn't simply have to move through space. It has to become an entire world. That changes everything. On Earth, we rarely notice how completely our survival depends on the planet beneath our feet. Forests recycle oxygen. Oceans regulate climate. Microorganisms break down waste and return nutrients to the soil. Countless natural systems operate together every second, creating an environment where life can continue almost effortlessly. We didn't build those systems. We inherited them. A starship has no such luxury. Every one of those life support systems must be recreated inside a machine built by human hands. Air has to be recycled with extraordinary efficiency. Water cannot simply be consumed and replaced. It must circulate endlessly through closed systems. Food has to be grown or carefully manufactured for years without failure. Waste becomes a resource rather than something that can simply be discarded. In deep space, nothing can be wasted because there is nowhere to replace it. The International Space Station has already taught scientists how difficult this is. Astronauts recycle much of their water, monitor air quality constantly, and depend on carefully maintained life support equipment every single day. Even with continuous support from Earth, regular cargo missions, and teams of engineers monitoring every system around the clock, keeping a handful of astronauts alive remains an incredibly complex task. Now imagine doing the same thing without Earth. No supply launches, no replacement parts, no emergency evacuation, no mission control capable of solving every unexpected problem. A true interstellar starship would have to survive completely on its own, perhaps for generations. Every system would need to keep functioning despite wear, aging, and unpredictable failures. The ship wouldn't simply carry life. It would have to become a completely self-sustaining ecosystem, capable of supporting an entire community far beyond the reach of human civilization. And ecosystems are remarkably fragile. History shows us that even small changes can produce consequences nobody expected. Introduce one new species into an environment, and the entire food chain can shift. Remove a tiny microorganism, and nutrients stop cycling correctly. On Earth, nature usually adapts because it has billions of organisms and vast ecosystems to absorb mistakes. Inside a spacecraft, there is no such safety net. Every balance must be carefully maintained because there is no second planet waiting outside the airlock. This is why many scientists believe the greatest challenge of interstellar travel isn't propulsion at all. It's reliability. Can a machine built by humans continue functioning perfectly for 50 years? 100 years? 500 years? Perhaps even longer? Those questions have no easy answers because humanity has never built anything that has successfully supported generations of people in complete isolation. Every civilization in history has relied on an entire planet. A starship would have to replace that planet with a collection of machines, pipes, computers, and carefully engineered biological systems that simply cannot afford to fail. And yet, even if we somehow solve every engineering challenge, even if we create the perfect closed ecosystem capable of sustaining life indefinitely, another problem still remains. It isn't mechanical. It isn't biological. It's human. Because surviving deep space isn't just about keeping the body alive. It's about keeping the mind alive as well. Even if a future starship could recycle every drop of water, produce its own food, repair its own machinery, and protect its crew from the hazards of deep space, one challenge would still remain beyond the reach of engineering. The human mind. For almost every moment of our existence, humanity has lived beneath an open sky. We've evolved surrounded by changing landscapes, fresh air, weather, oceans, forests, and the constant presence of other living things. Our brains developed on a planet that is endlessly dynamic. Every sunrise is slightly different. Every season changes the world around us. Even silence on Earth is never truly silent. A starship would erase almost all of that. Imagine waking up every morning inside the same corridors, walking the same hallways, seeing the same walls, and speaking to the same small group of people for years without interruption. Outside the windows, nothing changes except the slow movement of distant stars. There are no mountains to climb, no oceans to visit, no rainstorms to watch, and no cities waiting over the horizon. Every direction leads to exactly the same view, an endless darkness that stretches for trillions of kilometers. At first, that routine might seem manageable. After all, people spend months in submarines, research stations, and even aboard the International Space Station. But those missions all share one comforting truth. Everyone knows they are going home. That single idea changes everything. Astronauts aboard the International Space Station may spend 6 months in orbit, but Earth is always visible through the windows. Families remain only a video call away. If a serious emergency occurs, returning home is difficult, but it is possible. The same is true for researchers living through Antarctic winters. Isolation is challenging, yet they know rescue will eventually arrive. A real interstellar mission offers no such promise. The farther a spacecraft travels from Earth, the less meaningful the idea of home becomes. Communication delays grow longer every year until conversations become impossible. A message sent from Earth may take years to arrive. A reply could require years more. Eventually, entire generations may live and die before receiving answers to questions asked by their grandparents. At that point, the crew is no longer visiting another star. They have become their own civilization. Children born aboard the spacecraft would never experience Earth's gravity. They would know forests only through recordings. Oceans would exist only in history lessons. Birds, wind, rain, and open horizons would become stories passed down from people who had never actually seen them. To those future generations, Earth might feel less like a real place and more like an ancient legend. That creates a profound psychological challenge. Why should someone spend their entire life maintaining a mission they never chose? The first generation volunteers. The second generation inherits the mission. The third generation may begin asking whether the mission should continue at all. History suggests that societies remain stable when people share a common purpose. But what happens if that purpose slowly disappears? What happens if different generations begin disagreeing about the destination, the rules, or the sacrifices demanded by life aboard the ship? A starship isn't simply transporting people across space. It's transporting an entire society through centuries of isolation, where every disagreement unfolds inside a closed environment with nowhere else to go. This is why psychologists often argue that the greatest threat to an interstellar mission may not be mechanical failure. It may be social failure. A single conflict cannot simply be escaped. A divided community cannot simply move to another city. Every relationship, every disagreement, and every difficult decision remains trapped inside the same metal walls, drifting through the darkness between the stars. Suddenly, the challenge of interstellar travel looks very different. It's no longer just a question of physics. It's a question of human nature. Can people remain united across generations while surrounded by absolute isolation? Can culture survive centuries without contact with the civilization that created it? Can hope outlive the people who first launched the mission? Those questions remain unanswered because humanity has never attempted anything remotely comparable. And perhaps that's the most sobering realization of all. The first true starship won't simply test our technology. It will test whether human civilization itself can survive when Earth is no longer part of the equation. Before we can ask where a starship might travel, we first have to answer a far more difficult question. Could an isolated civilization remain human after centuries among the stars? By this point, the challenge of interstellar travel has changed completely. We began by asking whether a spacecraft could survive the journey. Then we asked whether human beings could survive inside that spacecraft. But now we arrive at an even stranger question, one that has almost nothing to do with engines, radiation, or life support systems. What happens when the people aboard stop thinking of themselves as passengers? What happens when they begin thinking of the ship as home? This is where the idea of a generation ship begins. Instead of building a spacecraft fast enough to reach another star within a single lifetime, humanity could build a world designed to travel for centuries. The people who launched the mission would never see its destination. Neither would their children, perhaps not even their grandchildren. The starship would become a moving civilization, carrying generation after generation across the immense darkness between the stars until, one day, descendants of the original crew would arrive at a planet their ancestors had chosen centuries earlier. At first, the concept sounds almost elegant. If physics refuses to let us travel faster, perhaps we simply learn to travel longer. But hidden inside that solution is one of the most profound psychological transformations humanity has ever imagined. The first generation would remember Earth. They would remember blue skies, changing seasons, oceans stretching to the horizon, and cities filled with billions of people. They would understand exactly what had been sacrificed to begin the mission, because they had lived the life that existed before it. Every day aboard the ship would be measured against memories of another world. The generations born later would have no such memories. To them, the spacecraft would not feel temporary. It wouldn't feel like a vehicle at all. It would feel like reality itself. The corridors would become streets. The agricultural decks would become countryside. The engineering sections would become distant industrial districts visited only by specialists. Children would grow up learning about Earth the same way we learn about ancient civilizations, through stories, photographs, and historical records describing a place no living person had ever seen. Eventually, something extraordinary could happen. Earth might stop feeling like home. It might become mythology. Imagine asking a child born 300 years into the voyage where they come from. They wouldn't point toward a planet orbiting an ordinary yellow star thousands of billions of kilometers behind them. They would point to the spacecraft itself. Every friend they've ever known, every lesson they've ever learned, every celebration, every tragedy, every birth, and every funeral has happened within the same enclosed world. Their identity wouldn't be tied to Earth. It would be tied to the ship. History tells us that cultures constantly evolve, even over relatively short periods of time. Languages change, traditions adapt, new beliefs emerge while old ones slowly disappear. Now imagine that process unfolding not across continents, but inside a completely isolated civilization with no outside influence for centuries. The society that eventually reaches another star may no longer resemble the one that launched from Earth. Its customs could be different. Its values could be different. It might even speak a different language. Some historians and sociologists have suggested that future generations might eventually question the mission itself. Why continue sacrificing resources for a destination chosen by people who died centuries ago? Why risk landing on an unfamiliar world when the spacecraft has become the only home anyone has ever known? To the descendants of the original crew, reaching another star may not feel like fulfilling humanity's dream. It may feel like abandoning their own civilization. This is a problem that no equation can solve. It isn't an engineering challenge. It's a question of identity. How do you preserve a shared purpose across 10 generations? How do you ensure that people continue believing in a mission they never volunteered for? And perhaps most importantly, do they even have a moral obligation to continue it? These aren't questions for physicists. They're questions for philosophers, psychologists, and every future generation that might one day be born aboard humanity's first true starship. Because the longer we think about generation ships, the stranger they become. They're not really spacecraft. They're civilizations traveling through the stars. And history has shown us that civilizations don't remain unchanged forever. The longer the journey lasts, the greater the chance that the destination itself will stop being the thing that matters. If a generation ship remains in space for hundreds of years, one uncomfortable possibility begins to emerge. The greatest threat to the mission may not come from outside the spacecraft at all. It may come from time itself. History has taught us a simple lesson. Civilizations change. Every society on Earth has transformed over the centuries. Languages evolve, traditions disappear, beliefs are replaced, and even the most important historical events slowly fade into legend. Now imagine that same process unfolding inside a spacecraft completely isolated from the rest of humanity. There are no new immigrants to reinforce old traditions, no contact with Earth, no shared global culture, only the people aboard the ship, passing stories from one generation to the next. How long before those stories begin to change? Imagine a child born 200 years into the journey. They learn in school that their distant ancestors came from a blue planet called Earth, launched this ship, and gave their descendants a single purpose: reach another star. To us, that sounds like history. To the child, it may sound like mythology. After all, no one alive has ever seen Earth. Every photograph was taken centuries ago. Every recording belongs to people who died long before their great-grandparents were born. At some point, the line between history and legend begins to blur. This isn't speculation. It's something humanity has experienced many times before. Entire civilizations have forgotten how their own monuments were built. Ancient technologies have disappeared for centuries before being rediscovered. Languages once spoken by millions have vanished completely. If those things can happen on a connected planet filled with libraries, universities, and billions of people, what might happen inside a closed society of only a few thousand individuals drifting through deep space? Perhaps the mission survives exactly as planned. Or perhaps it slowly transforms into something entirely different. A future generation might begin asking questions that no one on the launch crew ever imagined. Why should we continue sacrificing resources for a destination chosen hundreds of years ago? Why risk landing on an unknown planet when the ship already provides everything we need? Why leave the only world anyone alive has ever known? Those questions don't have obvious answers. From our perspective, the spacecraft is merely transportation. From their perspective, it is civilization itself. Every hospital, every classroom, every family memory, every friendship, and every tradition exists within its walls. To abandon the ship might feel less like reaching a destination, and more like abandoning home forever. And that changes the mission completely. Original crew imagined themselves as explorers. Their descendants may see themselves as citizens of an entirely new world. The starship stops being a vehicle and becomes a nation, one with its own culture, its own identity, and perhaps even its own politics. Disagreements that would seem minor on Earth could become existential in deep space. If one group wants to continue the journey while another wants to remain aboard the ship indefinitely, there is no nearby continent where they can separate. There is no neighboring country to move to. Every conflict must be resolved within the same enclosed world. Some researchers have even suggested that a generation ship could eventually develop social structures unlike anything that exists on Earth today. New holidays might celebrate milestones in the voyage rather than events from Earth's history. Children might grow up navigating by engineering decks instead of continents. The stars outside the observation windows could become the constellations of a completely new civilization, one that no longer thinks of itself as belonging to a distant planet orbiting an ordinary yellow star. By then, the mission would have achieved something nobody expected. It wouldn't simply have transported humanity across the galaxy. It would have created a new branch of humanity altogether. And that possibility forces us to confront one final question. If the people who finally arrive at another star no longer think of themselves as citizens of Earth, if their language, culture, and identity have all changed over centuries of isolation, can we still say the original mission succeeded? Or did humanity unknowingly create something entirely new? Because once a civilization spends enough time among the stars, the destination may no longer be the greatest transformation. The journey itself may redefine what it means to be human. And before we ask whether a real starship could survive deep space, we have to confront an even deeper mystery. What would thousands of years in the cosmos do to the human species itself? For thousands of years, human history has unfolded beneath the same sky. Every civilization, every language, every scientific discovery, and every moment of human evolution has taken place under Earth's gravity, inside Earth's atmosphere, protected by Earth's magnetic field. We often think of these conditions as normal because they are all we've ever known, but in reality, they are incredibly rare. They are the product of one very specific planet orbiting one very ordinary star. Remove humanity from that environment for centuries, and an unsettling question begins to emerge. Would we still remain the same species? At first, the answer seems obvious. Human DNA doesn't suddenly change because we leave Earth. A child born aboard a starship would still be genetically human. They would look like us, think like us, and share the same biological heritage. But evolution has never depended on a single generation. It works through countless small changes accumulating over enormous spans of time. And if a civilization spends hundreds, or perhaps thousands, of years living inside an artificial world, those small changes may begin to reshape humanity in ways no one can fully predict. The first difference would be gravity. Life on Earth evolved under a constant pull of one gravity for nearly 4 billion years. Every bone in your body, every muscle you use to stand, every beat of your heart has been shaped by that invisible force. Even astronauts living aboard the International Space Station begin experiencing dramatic physical changes after only a few months in microgravity. Their muscles weaken, their bones lose density, fluids shift toward the head, eyesight can change, and the body starts adapting to an environment it was never designed to inhabit. These effects can be reduced through exercise, but they cannot be ignored. Now imagine children who have never experienced Earth's gravity at all. If a generation ship failed to produce artificial gravity, or if it produced only a fraction of Earth's gravity, entire generations would grow up with bodies fundamentally different from ours. They might become taller as their spines develop under weaker gravitational forces. Their skeletons could become lighter. Their muscles might adapt to an environment where supporting body weight requires far less effort. Over centuries, natural selection and biological adaptation could begin favoring traits that make life aboard the ship easier rather than traits optimized for living on Earth. That creates an extraordinary possibility. The descendants of Earth's first interstellar travelers might eventually find Earth itself uncomfortable. Imagine asking someone born after 500 years in low gravity to walk across Earth's surface. Every movement would feel unusually heavy. Their heart would work harder. Their muscles would tire quickly. Even standing upright could become exhausting. The planet that launched humanity into the stars might become a place where its own descendants struggle to survive. Gravity, however, is only part of the story. A generation ship would also create one of the most genetically isolated populations in human history. Unlike Earth, where billions of people continuously exchange genes across continents, a starship would contain only a limited number of individuals. Maintaining genetic diversity would become one of the mission's greatest priorities. Scientists have already studied this problem, suggesting that future missions would require careful population planning, advanced reproductive medicine, and long-term genetic monitoring to reduce the risks associated with small populations. Even with perfect planning, isolation changes evolution. Every generation born aboard the ship would inherit not only genes, but also an environment completely unlike anything experienced by their ancestors. Different diets, artificial lighting, recycled ecosystems, altered day-night cycles, and entirely new social structures could all influence how future generations develop. Some changes might be subtle. Others could become surprisingly significant over centuries. Perhaps the most fascinating possibility is that none of these transformations would happen because humanity intended them. They would happen simply because the environment changed. Evolution has never planned ahead. It doesn't ask where a species wants to go. It simply favors whatever survives under present conditions. A starship crossing interstellar space would become a completely new environment, quietly shaping the people living inside it with every passing generation. And that leads to a profound realization. The first humans to reach another star may not resemble the people who launched the mission, not because technology changed them, but because the journey itself did. The destination may be another solar system. But the greatest transformation could happen long before the ship ever arrives. Section 7b, Will Humans Still Be Human? Words. If a generation ship remains isolated for centuries, evolution may slowly reshape the human body, but an even more profound question follows. What happens to the human mind? Biology determines how we survive. Culture determines who we are. Every belief, tradition, language, and value we hold today is the product of thousands of years spent living together on Earth. We often assume those things are permanent, but history tells a very different story. Civilizations rise and fall, religions evolve, languages split into entirely new languages, customs that once seemed unchangeable disappear within only a few generations. Human identity has never been fixed, it has always been adapting. Now imagine that process unfolding in complete isolation. A child born aboard a starship would never watch birds crossing the sky because there would be no sky. They would never hear rain striking a rooftop or waves crashing onto a beach because there would be no oceans. Their understanding of nature would come from recordings made centuries earlier by people they would never meet. To them, forests, mountains, deserts, and thunderstorms might feel less like memories of home and more like scenes from an ancient documentary describing a world that no longer feels real. Eventually, Earth itself could become an idea rather than a place. Every generation would retell its history a little differently. Some details would be forgotten, others would become symbols. Stories about humanity's home planet might gradually take on the emotional weight of myths, preserving the spirit of the past while slowly losing the precise reality behind it. The people living aboard the ship would still know that Earth existed, but knowing something through history is very different from experiencing it yourself. Over enough time, an entirely new culture would emerge. The ship would develop its own traditions, its own celebrations, and perhaps even its own calendar based on the milestones of the journey rather than the seasons of Earth. Children might celebrate the anniversary of passing a nearby star instead of the anniversary of the spacecraft's launch. Navigation decks could become places of ceremony. Engineering crews might be viewed with the same respect that ancient civilizations reserved for farmers, because maintaining the life support systems would mean preserving life itself. Even language would refuse to stand still. Languages evolve surprisingly quickly. Compare modern English with the English spoken only a few hundred years ago, and many passages become difficult to understand. Extend that process across 500 or 1,000 years inside an isolated civilization, and the descendants of the original crew could be speaking a language that sounds completely unfamiliar to us. The mission logs recorded on the day of launch might eventually require translators for the very people they were written to inspire. This is not science fiction. It's exactly what history predicts. Human societies constantly transform because every generation inherits the world slightly differently than the one before it. A generation ship would accelerate that process by removing almost all outside influences. There would be no new cultures to interact with, no global communication network, and no contact with Earth to reinforce shared traditions. The civilization aboard the ship would slowly become something entirely unique. And then comes the most fascinating possibility of all. Imagine that after 700 years, the spacecraft finally enters orbit around another star. The descendants of the original crew prepare to step onto the first habitable planet humanity has ever reached beyond the solar system. They succeed. The mission is celebrated across history as one of humanity's greatest achievements. But are the people stepping onto that world truly the same humanity that launched the mission? Genetically, perhaps. Historically, certainly. Culturally, perhaps not. They may carry different beliefs, speak different languages, understand the universe through different traditions, and define home in ways their ancestors could never have imagined. From Earth's perspective, the mission created a distant colony. From the perspective of those arriving, they may see themselves as the first citizens of an entirely new civilization. Perhaps that was always inevitable. Perhaps interstellar travel was never just about reaching another star. Perhaps it was always about becoming something new. And that realization changes the entire meaning of the journey. Because if humanity ever succeeds in crossing the immense darkness between the stars, the greatest discovery may not be another planet waiting in the distance. The greatest discovery may be the realization that the journey itself quietly transformed the explorers into a different version of humanity. And that raises one final question, one that reaches far beyond biology, engineering, or even civilization itself. If a starship can survive for centuries, what happens when it survives for millions, or even trillions of years? For most of this documentary, we've imagined a starship traveling through a universe that stays more or less the same. The stars remain where they are. The destination patiently waits. The only challenge is surviving the journey. But the universe doesn't work that way. The moment a spacecraft leaves the solar system, it isn't simply traveling through space. It's traveling through a cosmos that is constantly changing. Every star is moving. Every galaxy is moving. Even the Milky Way itself is racing through the universe at extraordinary speed. The destination you choose today will not be in exactly the same place tomorrow, next year, or a million years from now. That sounds like a small detail. In reality, it changes everything. Take our own sun as an example. Although it feels perfectly still from Earth, the sun is actually orbiting the center of the Milky Way at nearly 220 kilometers every second. At that speed, our solar system completes one orbit around the galaxy roughly every 230 million years. During the time dinosaurs ruled Earth, the sun occupied an entirely different region of the Milky Way. By the time humanity disappears, whenever that may be, the solar system will have moved again. And the sun isn't unique. Every nearby star follows its own path through the galaxy. Some move slightly faster, others travel in different directions. They drift past one another over millions of years like ships crossing a vast ocean. The familiar constellations we recognize today are only temporary arrangements. Given enough time, Orion, Ursa Major, and every pattern humanity has ever traced across the night sky will slowly dissolve into completely new shapes. For everyday life, those changes are far too slow to notice. For an interstellar mission lasting centuries, they become impossible to ignore. Imagine launching a starship toward a nearby system that appears perfectly positioned today. During the hundreds of years your spacecraft spends traveling, both your solar system and the destination continue moving through the galaxy. Fortunately, astronomers can predict those motions with remarkable accuracy over relatively short timescales, allowing future spacecraft to aim not at where a star is today, but where it will be when they finally arrive. In other words, a real starship wouldn't chase its destination. It would intercept it. This idea is surprisingly familiar. When NASA sends a spacecraft to Mars, engineers don't aim at the planet's current position because Mars won't still be there when the spacecraft arrives. Instead, they calculate where Mars will be months later and send the spacecraft toward that future location. Interstellar navigation follows exactly the same principle, but on a scale so vast that the calculations involve centuries instead of months. Yet even that isn't the whole story. Because while stars move through the Milky Way itself is moving through an even larger cosmic landscape. Our galaxy and the neighboring Andromeda galaxy are slowly falling toward each other under the force of gravity. In about 4.5 billion years, they will begin an enormous galactic collision, not a catastrophic crash of stars, but a graceful merging of two spiral galaxies into something entirely new. Fortunately, no starship traveling for a few centuries would need to worry about witnessing that event. But it reveals an important truth. Nothing in the universe is permanent. Not stars, not galaxies, not even the galaxy we call home. The longer a journey lasts, the less familiar the cosmos becomes. A civilization traveling for hundreds or thousands of years wouldn't simply be crossing distance. It would be crossing time on a cosmic scale. The night sky their ancestors left behind would slowly transform into something unrecognizable. Constellations would shift, neighboring stars would drift away while others moved closer. Even the galaxy itself would continue evolving around them. Suddenly, another unsettling realization appears. A starship traveling long enough may eventually return to a universe that no longer resembles the one it departed. And if the cosmos itself never stops changing, what happens to a spacecraft that refuses to stop traveling? Could it continue drifting for millions, billions, or even trillions of years after every civilization that built it has disappeared? That question takes us beyond engineering and beyond human history. It takes us into the deep future of the universe itself. So far, we've imagined a starship surviving for centuries, perhaps even millions of years. We've watched it outlive generations, civilizations, and maybe even the planet that launched it. But if we're asking how long a real starship could survive in deep space, then we can't stop at human timescales. We have to start thinking like the universe. Because while human history is measured in thousands of years, the cosmos measures time in billions. And on those timescales, even the stars begin to die. It's easy to think of stars as permanent. Every civilization in history has looked up at the same night sky, and the brightest stars appear almost unchanged. They feel eternal. But that feeling is an illusion created by the shortness of a human lifetime. Stars are not eternal. They are living objects with beginnings, lifetimes, and endings. Like everything else in the universe, they are slowly moving toward a future they cannot escape. Our own sun is no exception. Right now, every second, the sun converts nearly 600 million tons of hydrogen into helium, releasing the energy that warms our planet and makes life possible. It has been doing this for about 4.6 billion years, and it will continue for roughly another 5 billion years. From our perspective, that sounds almost infinite. To the universe, it's only the middle of the story. As the sun ages, the balance inside its core will slowly change. Hydrogen fuel will become harder to find. Gravity will begin compressing the core more intensely, while the outer layers expand farther into space. Billions of years from now, the familiar yellow star that gave birth to every human civilization will transform into a red giant hundreds of times larger than it is today. The consequences will be extraordinary. Mercury will almost certainly disappear. Venus will almost certainly disappear. And Earth's. Its ultimate fate remains the subject of scientific research, but whether our planet is swallowed directly or left as a scorched, lifeless world orbiting a dying star, the Earth we know today will be gone forever. Long before that final moment arrives, rising solar temperatures are expected to make our planet increasingly hostile to complex life. Eventually, humanity will face a choice: leave or disappear. This is one of the deepest reasons scientists take interstellar travel seriously. It isn't simply about curiosity or exploration. On the longest timescales imaginable, remaining on one planet means accepting the fate of that planet. Every civilization that hopes to survive for billions of years must eventually learn to move beyond its birthplace. But even escaping the sun doesn't solve the problem. Every star in the galaxy follows its own life cycle. Some burn quietly for trillions of years. Others exhaust their fuel in only a few million years before exploding as spectacular supernovae, scattering heavy elements across space and giving birth to the next generation of stars. The Milky Way is constantly recycling itself, replacing old stars with new ones in a process that has continued for more than 13 billion years. A starship traveling long enough would witness that cycle firsthand. Entire constellations would slowly vanish as familiar stars reached the ends of their lives. New stars would ignite inside distant clouds of gas and dust. Regions of the galaxy that once glowed brightly would grow dark, while previously invisible stellar nurseries burst into light. The night sky itself would become unrecognizable, not because the ship had moved so far, but because the universe had changed around it. For the crew aboard such a vessel, the passage of cosmic time would become impossible to ignore. The galaxy they left behind would no longer exist in the form they remembered. And yet, astonishingly, even this isn't the end of the story. Because stars are only temporary residents of the cosmos. If enough time passes, the Milky Way itself will begin running out of the raw material needed to create new ones. One by one, the lights of the universe will start going out. The brilliant galaxies filling today's night sky will slowly grow darker, quieter, and colder. The question is no longer whether a starship can survive for centuries. The question has become far more unsettling. Could it survive in a universe where the stars themselves are disappearing? Imagine looking out from the observation window of a starship, not after a few decades or even a few million years, but after trillions of years have passed. The universe would be almost unrecognizable. Today, the night sky is filled with brilliant stars because we happen to live during one of the most active periods in cosmic history. Galaxies are still rich with cold clouds of hydrogen, the raw material from which new stars are born. Across the universe, countless stellar nurseries continue lighting up the darkness, ensuring that every time one star dies, another eventually takes its place. But this era will not last forever. Every new star consumes a little more of the galaxy's remaining fuel. Unlike the fuel in a car, hydrogen cannot simply be manufactured once it's gone. It was created during the earliest moments of the universe, and although dying stars recycle part of it back into space, each generation locks more material away inside white dwarfs, neutron stars, black holes, and countless dead stellar remnants. Slowly, almost imperceptibly, the Milky Way is spending a resource it can never fully replace. For billions of years, that loss hardly matters. For trillions of years, it changes everything. Astronomers believe there will come a time when galaxies stop producing new stars altogether. The giant clouds of gas that once glowed with the birth of suns will gradually disappear. The spectacular stellar nurseries that fill modern telescopes with breathtaking images will become silent. One by one, the familiar lights of the cosmos will fade, not because they explode, but because nothing new is there to replace them. The universe won't suddenly go dark. It will simply grow quieter. Imagine being alive to witness that transformation. Generation after generation, fewer bright stars would appear in the sky. Entire regions of the galaxy that once shimmered with young blue suns would become dominated by ancient, fading stars nearing the ends of their lives. The cosmos wouldn't end with a dramatic explosion. It would age. Just as a forest slowly changes when no new trees are allowed to grow, the galaxy would become a place filled mostly with old survivors. Red dwarf stars, the smallest and longest-lived stars in the universe, would continue shining for astonishing lengths of time. Some are expected to survive for trillions of years, making them the final natural sources of starlight long after larger stars like our Sun have vanished. If a starship somehow endured into that unimaginably distant future, its crew would witness a universe unlike anything humanity has ever known. There would be fewer destinations, fewer habitable systems, fewer opportunities to find warmth and light. The galaxy itself would begin feeling old. And yet, even in that fading universe, gravity would continue shaping the future. Stars would still orbit the galactic center. Black holes would continue swallowing wandering matter. Occasional collisions between dead stellar remnants would briefly illuminate the darkness before fading once again. Life, if it still existed anywhere, would become increasingly isolated, separated by distances that seemed to grow larger with every passing age. For a civilization traveling between the stars, hope would become a rarer resource than fuel. Every generation would inherit a cosmos with fewer lights than the one before. Eventually, a haunting realization would settle over the survivors. They were born during the brightest chapter in the history of the universe, and they were living long enough to watch that chapter come to an end. But even this isn't the final act. As extraordinary as trillions of years may sound, they represent only the beginning of the universe's future. Beyond them lies a timescale so vast that almost every star will have disappeared, galaxies themselves will begin to unravel, and darkness will become the dominant feature of reality. If a starship could somehow continue drifting through that unimaginable future, it would no longer be crossing a galaxy filled with stars. It would be crossing the ruins of a dying cosmos. And that leaves us with one final question. How long can anything survive when the universe itself is running out of light? By now, our journey has carried us far beyond anything a human civilization has ever experienced. We've watched stars grow old, galaxies evolve, and the brilliant age of starlight slowly begin to fade. But if a real starship somehow continued drifting through deep space, surviving not for thousands or even trillions of years, another reality would eventually emerge. The greatest threat would no longer be distance. It would be time itself. Human history has conditioned us to believe that the universe is permanent. Mountains seem eternal, oceans appear timeless, even galaxies look fixed and unchanging, but every discovery in modern astronomy points toward the same conclusion. Nothing lasts forever. Not stars, not planets, not galaxies. Given enough time, the entire architecture of the cosmos begins to come apart. This process doesn't happen violently. There is no single moment when the lights suddenly switch off. Instead, the universe slowly becomes less interesting. Every billion years, there are fewer bright stars. Every trillion years, there are fewer places where new stars can form. Every unimaginable stretch of time removes another piece of the cosmic landscape until the universe begins to resemble a vast museum filled with ancient relics instead of living worlds. Imagine standing aboard a starship during this distant future. Outside the observation windows, the familiar ribbon of the Milky Way has almost disappeared. The brilliant clouds of young stars that once filled the galaxy are gone. Most of the light comes from old, fading stellar remnants that have been cooling for longer than human language has existed. Entire regions of space that were once alive with activity now appear almost perfectly dark. Silence has become the natural state of the cosmos. But something even stranger is happening. The expansion of the universe, the same expansion that began with the Big Bang, is still continuing. In fact, it isn't slowing down, it is accelerating. For decades, astronomers assumed gravity would gradually slow the expansion of the cosmos. Instead, observations revealed something astonishing. The galaxies are moving away from one another faster and faster, driven by an unknown phenomenon we call dark energy. We still don't fully understand what dark energy is, but we can observe its effects. Every billion years, distant galaxies drift farther beyond our reach, carrying their light away forever. A civilization living in this far future would experience a profoundly different universe. Today, our telescopes can see hundreds of billions of galaxies spread across the observable cosmos. Future astronomers, living trillions of years from now, may see almost none of them. As space continues expanding, those distant galaxies will eventually move beyond the observable horizon. Their light will never reach us again. One by one, the universe will erase its own history. Imagine being born in that distant age. You look into the night sky and see only the stars belonging to your own galaxy. Every other galaxy has disappeared beyond the expanding edge of the observable universe. You have no evidence that they ever existed. The Big Bang itself becomes almost impossible to detect. The cosmic clues that allowed humanity to understand its origins quietly vanish. Future scientists might honestly conclude that their lonely galaxy is the entire universe. Not because they lack intelligence, but because the evidence has disappeared. This is one of the most astonishing predictions in modern cosmology. The universe doesn't simply grow older. It slowly hides its own past. A starship drifting through this future would witness that transformation firsthand. Every million years, fewer galaxies decorate the darkness. Every billion years, the cosmos grows more isolated. Every unimaginable stretch of time leaves the ship surrounded by an emptiness even deeper than the one humanity feared at the beginning of this documentary. And perhaps that's the greatest irony of all. We began by asking how long a real starship could survive in deep space. But now deep space itself is changing. The ocean through which the ship travels is slowly becoming larger, darker, and infinitely more lonely. And if the expansion of the universe never stops, then one final destination awaits every starship ever built. Not another galaxy, not another civilization, but absolute isolation itself. Imagine that your starship survives everything. It survives the crushing distances between the stars. It survives radiation, dust, mechanical failures, and the rise and fall of countless generations. It even survives the slow aging of the galaxy itself. After trillions of years, it is still drifting through the darkness, carrying the last echoes of a civilization that disappeared so long ago that even its name has been forgotten. Surely at that point, the journey is over. But the universe isn't finished. Because the future of the cosmos isn't defined only by dying stars. It's defined by expanding space. This is one of the strangest discoveries modern astronomy has ever made. Every second, the fabric of the universe stretches a little more. Galaxies aren't simply flying through space. Space itself is growing between them. Imagine drawing tiny dots on the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot, not because the dots are moving across the rubber, but because the rubber itself is expanding beneath them. That is remarkably similar to what our universe has been doing for more than 13 billion years. And the expansion isn't slowing. It's accelerating. Every passing moment carries distant galaxies farther beyond our reach. Light that could once have reached us will eventually never arrive. Entire clusters of galaxies are quietly disappearing behind a cosmic horizon, not because they have ceased to exist, but because space is expanding too rapidly for their light to ever catch up. The universe is slowly becoming a collection of isolated islands. Today, we live during a remarkably fortunate era. Our telescopes reveal an enormous cosmic web connecting hundreds of billions of galaxies. We can reconstruct the history of the universe because the evidence still surrounds us, but that window will not remain open forever. Imagine a civilization living 100 trillion years from now. They build observatories more powerful than anything humanity has ever imagined. They search the skies hoping to understand where they came from. Yet no matter how advanced their technology becomes, they find almost nothing beyond their own galactic neighborhood. Every distant galaxy has slipped beyond the observable horizon. To them, the universe appears small, quiet, alone. The greatest discoveries of modern cosmology become impossible, not because they were wrong, but because the evidence has vanished forever. In a strange sense, the universe begins deleting its own memories. Now imagine our starship continuing through that lonely future. There are no bustling galaxies ahead. No bright spiral systems waiting on the horizon. No nearby civilizations exchanging signals across intergalactic space. Every million years, the darkness grows deeper. Every billion years, another piece of the visible universe quietly disappears. Eventually, the crew, if any remain, or the ship's autonomous systems, would realize something extraordinary. They are no longer traveling toward anything. They are simply drifting through an expanding emptiness that becomes larger with every passing age. This is the fate that awaits not just one spacecraft, but every object that isn't gravitationally bound to something larger. Over unimaginable spans of time, the universe becomes increasingly fragmented. Islands of matter remain together locally, but the vast oceans between them continue expanding forever. The farther our starship travels, the less there is to find. And perhaps that is the greatest reversal in this entire story. At the beginning of this documentary, deep space seemed terrifying because it looked empty. Now we understand something even more unsettling. It wasn't truly empty. It was alive with stars, galaxies, and possibilities. The real emptiness belongs to the future. A future where the distances between galaxies become so enormous that light itself can no longer bridge them. A future where every surviving civilization looks into the sky and wonders if it is completely alone. And yet, even that is not the final chapter. Because beyond the age of fading galaxies lies a future so unimaginably distant that the universe itself begins approaching its ultimate fate. If our starship somehow survives long enough to witness that moment, it won't simply outlive humanity. It may outlive everything that has ever shined. For almost the entire history of the universe, light has defined reality. Every civilization has measured time by the rising and setting of a star. Every planet capable of supporting life has depended on the warmth of sunlight. Even the greatest discoveries in astronomy have been made possible because distant stars and galaxies filled the darkness with light. It's easy to believe that this is simply what the universe is. A place filled with countless shining suns. But that picture is only temporary. If our starship could somehow continue its journey, not for billions of years, but for trillions, it would witness one of the greatest transformations the cosmos will ever experience. The gradual end of the age of stars. At first, nothing dramatic happens. The largest stars have already disappeared long before this era begins. Their lives were spectacular but short, burning through their nuclear fuel in only a few million years before ending in violent supernova explosions. Stars like our own sun survived much longer, shining for roughly 10 billion years before expanding into red giants and leaving behind slowly cooling white dwarfs. For a while, smaller stars continue carrying the universe forward. These are the red dwarfs, the smallest true stars ever formed. They aren't particularly bright. Many are barely visible from enormous distances. Yet what they lack in brilliance, they make up for in endurance. Because they burn their fuel so slowly, astronomers estimate that the smallest red dwarfs can continue shining for ** trillions of years, making them the longest-lived stars the universe has ever produced. If any civilization survives into this unimaginably distant future, these ancient red dwarfs may become the final islands of natural light in an otherwise darkening cosmos. Imagine standing inside the observation deck of our starship during this era. The brilliant spiral arms that once filled the Milky Way have faded into history. Young blue stars no longer illuminate vast clouds of gas because almost all of that gas has already been consumed. The spectacular nebulae photographed by telescopes like Hubble and James Webb exist only in ancient archives preserved by civilizations long gone. Outside the windows, the galaxy feels older, quieter. The sky is no longer crowded with countless bright stars. Instead, scattered points of faint red light glow across immense distances, each one representing one of the last stellar survivors in the universe. The darkness isn't absolute. But for the first time since the birth of the cosmos, darkness is beginning to win. Our starship continues moving. Its engines may have fallen silent ages ago, leaving gravity alone to guide its path through interstellar or perhaps intergalactic space. The civilization that built it may have disappeared billions of years earlier. Its language may have been forgotten. its mission may have ended beyond anyone's memory. Yet the spacecraft remains. A silent object drifting through a universe that is slowly exhausting its ability to produce light. Eventually, even the oldest red dwarfs reach the ends of their extraordinary lives. Unlike massive stars, they don't explode. They simply consume the last of their hydrogen, fade, and leave behind stellar remnants that emit almost no visible light. One by one, the final natural beacons of the cosmos begin disappearing. No sunrise replaces them. No younger generation of stars takes their place. The factories that once created new suns have long since shut down. This is a future unlike anything humanity has ever experienced. For billions of years, the universe renewed itself. Stars died, but new stars were always born from the gas and dust left behind. It was a cosmic cycle of destruction followed by creation. Now that cycle has ended. Not because something catastrophic happened, but because the raw material has simply been used up. It's a strangely peaceful ending. The universe doesn't collapse into chaos. It grows old. The same way an ancient forest slowly changes after the last young trees stop growing, the cosmos becomes a place populated almost entirely by aging remnants of a brighter past. If someone could look across the galaxy during this era, they would no longer see rivers of starlight stretching across the heavens. They would see enormous regions where almost nothing shines at all. For our lonely starship, the journey has become almost surreal. There are fewer landmarks to navigate by, fewer destinations worth reaching, fewer signs that this was once a universe overflowing with energy and creation. Distance itself begins losing meaning. When nearly every direction looks the same, traveling another billion kilometers or another billion light years changes almost nothing. The darkness is simply deeper. And yet, astonishingly, the story still isn't over. Because even after the last stars fade, the universe refuses to become completely empty. Scattered throughout the darkness are objects that survive far longer than any star ever could. White dwarfs continue cooling for unimaginable spans of time. Neutron stars silently orbit through the remnants of ancient galaxies. And hidden among them are the strangest objects the universe has ever created. Black holes. Unlike stars, black holes don't shine because of nuclear fusion. They don't require hydrogen to keep existing. They are sustained by gravity itself, making them among the longest-lived structures in the entire cosmos. As the age of starlight finally comes to an end, a new era quietly begins. An era where almost every remaining giant object in the universe is no longer a star, but a black hole. If our starship somehow survives long enough to witness that distant future, it will enter a cosmos unlike anything humanity has ever imagined. A universe where darkness has become the rule. And black holes are the last great giants still standing. When the final stars have faded, the universe enters a chapter unlike any that came before. For the first time since the Big Bang, light is no longer the dominant feature of reality. Darkness is. Not the familiar darkness of a moonless night, where distant stars still fill the sky. This is a deeper darkness, one stretching across galaxies that no longer produce new suns, across empty space where the last red dwarfs have already exhausted their fuel. The brilliant universe that once gave birth to planets, oceans, and civilizations has become astonishingly quiet. Yet it isn't completely empty. Scattered throughout this immense darkness are objects so extreme that they have survived every cosmic catastrophe the universe could produce. Black holes. Ironically, these invisible objects become the largest remaining structures in an aging cosmos. Billions of years earlier, They were born from collapsing stars or from the chaotic centers of young galaxies. At the time, they seemed like destructive anomalies, regions where gravity had become so powerful that not even light could escape. But as the universe grows older, their role quietly changes. They become the final monuments of the stellar age. Imagine our starship still drifting through this unimaginable future. The observation windows reveal almost no starlight. Instead, the darkness is interrupted only by subtle distortions in the background, where gravity bends the paths of the few remaining photons crossing the cosmos. The ship no longer navigates by constellations because there are almost none left. Instead, gravity itself becomes the only reliable guide through a universe that has nearly forgotten what light looks like. It is a haunting transformation. The objects humanity once feared have become the last giants still standing. For an unimaginably long time, black holes continue existing almost unchanged. They merge with one another, quietly swallowing the occasional wandering star, white dwarf, or neutron star that passes too close. Each collision releases one final burst of gravitational waves before silence returns once again. To an outside observer, it might appear that black holes are eternal. But modern physics suggests something even stranger. In the 1970s, physicist Stephen Hawking discovered that black holes may not last forever. By combining quantum theory with gravity, he showed that black holes are expected to emit an incredibly faint form of thermal radiation, now known as Hawking radiation. The effect is unimaginably small for large black holes. In fact, the supermassive black holes at the centers of galaxies would require timescales so enormous that ordinary numbers become meaningless before they completely disappear. From a human perspective, they effectively live forever. But not forever in the language of physics. Over unimaginable spans of time, every black hole slowly loses a tiny amount of energy. The process is so slow that even after trillions upon trillions of years, almost nothing appears to change. Yet the laws of thermodynamics are remarkably patient. Given enough time, even black holes begin to fade. The idea is almost impossible to comprehend. For billions of years, black holes represented permanence. They survived exploding stars, galactic collisions, and the slow death of starlight itself. Entire civilizations could rise and vanish, while these cosmic giants remained almost untouched. And then, silently, the universe begins taking them away as well. Our lonely starship continues drifting. If it somehow remains intact through these inconceivable ages, it witnesses something no intelligent civilization was ever expected to see. One by one, the last great engines of gravity disappear. No explosion marks their passing. No brilliant flash lights the darkness. Each black hole simply radiates away an almost immeasurable amount of energy until, after timescales beyond imagination, nothing remains. By now, the cosmos has entered an era unlike anything that existed before. No shining galaxies. No living stars. No growing planetary systems. Not even black holes dominate the landscape anymore. Only an immense, cold universe filled with scattered particles, faint radiation, and extraordinary emptiness. Some theoretical models suggest that, over even greater stretches of time, matter itself could continue changing in ways we still don't fully understand. One possibility proposed in certain theories is proton decay, in which the particles making up ordinary matter may eventually break apart. It's important to note that this has never been observed, and physicists still don't know whether it actually occurs. If it does, however, then the distant future of the universe becomes even stranger, as the familiar matter that built planets, stars, and even spacecraft would slowly disappear. Whether proton decay happens or not, one conclusion remains remarkably consistent across modern cosmology. Nothing material lasts forever. Not civilizations, not planets, not stars, not even black holes. And suddenly, our original question begins to sound completely different. We asked how long a real starship could survive in deep space. The answer is no longer measured in centuries, or millions of years, or even trillions. It is measured against the lifetime of the universe itself. Because eventually, every journey reaches a destination, not because the traveler decides to stop, but because the cosmos itself changes beyond recognition. And that leaves us with one final mystery. If even black holes eventually disappear, what is left for a starship to travel through? We've now traveled farther into the future than almost any story ever attempts. We've watched civilizations disappear. We've watched stars die. We've watched galaxies grow dark. We've even reached the unimaginable era where black holes, the most durable objects in the universe, begin their own slow disappearance. So now we're finally ready to answer the question that started this entire documentary. How long could a real starship survive in deep space? At first, the answer seems almost unbelievable. Much longer than humanity itself. Longer than Earth's. Longer than the Sun. Perhaps even longer than the Milky Way as we know it. But forever? No, because every object in the universe obeys one law that has never been observed to fail. Entropy. It's a word that appears throughout physics, yet its meaning is surprisingly simple. Left alone, every system naturally drifts toward greater disorder. A perfectly organized structure slowly becomes less organized. Energy spreads out, materials weaken, order gives way to randomness. It's why abandoned buildings collapse, why mountains slowly erode, and why even the brightest stars eventually exhaust the fuel that allows them to shine. A starship would be no different. Even if its engines were switched off forever, time would continue working against it. Imagine our spacecraft drifting through the darkness after its mission has ended. At first, it appears almost unchanged. There is no atmosphere to rust its metal, no wind to wear away its surface, no rain to corrode its structure. Space seems strangely protective compared to Earth. But appearances can be deceiving. Interstellar space is not empty. For billions of years, tiny particles of dust continue striking the hull at extraordinary speeds. Each collision is almost insignificant on its own, removing only microscopic amounts of material. But the universe has something humanity never does. Unlimited time. After millions of years, the damage is almost impossible to notice. After billions, small scars begin accumulating across the spacecraft's surface. After trillions, even the strongest materials ever engineered begin revealing the effects of an endless stream of microscopic impacts. Radiation tells a similar story. Throughout this documentary, we've explored cosmic rays capable of passing through spacecraft as though the walls barely existed. Individually, they rarely cause catastrophic damage. Instead, they slowly alter atoms, weaken electronics, and disrupt molecular structures one tiny interaction at a time. The process is almost invisible. But invisibility has never meant harmlessness. Over unimaginable stretches of time, every component aboard the spacecraft would slowly change. Protective coatings degrade, electronic memories become unreliable. Structural materials accumulate defects so small that no human instrument today could easily detect them. None of these changes happen overnight. The universe is remarkably patient. It doesn't need catastrophic failures. It simply waits. Even if some future civilization mastered self-repairing materials, and autonomous maintenance systems, another problem would eventually appear. Energy. Every machine requires it. Every repair consumes it. Every active system must draw power from somewhere. During the journey, that power might come from nuclear reactors, fusion technology, or energy harvested from nearby stars. But what happens after the stars themselves disappear? What happens when the surrounding universe grows too dark and too cold to provide meaningful energy at all? Eventually, every repair system falls silent. Not because it malfunctioned, because there is nothing left to power it. From that moment onward, the spacecraft enters a slow, irreversible decline. Doors remain closed forever. Computers stop calculating. Sensors stop observing. Transmitters stop transmitting. Whatever intelligence once guided the mission becomes only silent circuitry, drifting through an ancient cosmos. And yet, even then, the ship doesn't immediately disappear. Its structure may continue coasting through space for inconceivably long periods, carried only by inertia and gravity. It becomes less like a spacecraft and more like a fossil, a relic from an era when the universe was young enough to contain civilizations capable of dreaming about the stars. Perhaps that's the strangest realization of all. A real starship doesn't fail because space is violent. It fails because time never stops. The enemy was never distance. It was always duration. Every additional year gives entropy another opportunity to reshape the machine. Every passing billion years allows another microscopic imperfection to accumulate. Every unimaginable age brings the spacecraft one step closer to silence. Eventually, the difference between a functioning starship and a drifting fragment of metal disappears entirely. Not with an explosion, not with a collision, but through the quiet persistence of physical law. And maybe there's something profoundly beautiful about that. The universe doesn't destroy its creations in anger. It simply allows time to complete the work that began the moment those creations first came into existence. Every star, every planet, every civilization, every spacecraft, all become part of the same cosmic story. Which means our final answer isn't simply about engineering. It's about existence itself. No real starship can survive forever, because nothing in the known universe does. But perhaps forever was never the goal. Perhaps the true achievement isn't escaping time. It's leaving behind something that continues its journey long after its creators are gone. And there is one spacecraft, built by human hands nearly half a century ago, that is already doing exactly that. Its name is Voyager 1. Right now, as you're watching this documentary, Voyager 1 is still traveling. It isn't racing toward another star. It isn't searching for alien civilizations. It isn't following a carefully planned destination. It is simply moving forward, 1 second at a time, carrying humanity farther into deep space than anything we have ever built. In many ways, Voyager has already become exactly what we imagined throughout this journey. A real starship, not because it's carrying thousands of people across the galaxy, but because it has begun doing something no human being can ever experience for themselves. It is traveling into a future that none of its creators will ever see. Every engineer who helped design Voyager understood one simple truth. The spacecraft would outlive them, but few could have imagined just how extraordinary that statement would become. Long after today's nations have changed beyond recognition. Long after our cities have been rebuilt countless times. long after every person alive today has become part of history. Voyager will still be moving. Eventually, its instruments will fall silent. The tiny nuclear power source that has kept the spacecraft alive for decades will no longer produce enough electricity to operate its scientific equipment. One by one, the systems that allowed Voyager to communicate with Earth will permanently shut down. The final signal will arrive. Mission Control will listen. And then, silence. From that moment forward, Voyager will never speak again. Not because it has stopped existing, but because there will simply be no voice left. Yet something remarkable happens after the silence. The journey continues. Without engines, without commands, without anyone watching. Gravity alone will carry the spacecraft through the Milky Way for millions of years. It will slowly pass distant stars, drift through changing regions of the galaxy, and witness a future that no living mind will ever observe. It will become one of countless silent travelers, moving through a cosmos that never stops changing. Perhaps one day it will pass near another star. Perhaps it will wander through empty interstellar space forever. Perhaps it will orbit the galaxy until the galaxy itself no longer resembles the one we know today. No one can say. And somehow, that uncertainty is the most beautiful part of the story. Because Voyager was never really built to arrive somewhere. It was built to explore, even if no one is there to witness the exploration. Bolted to the side of the spacecraft is an object unlike any other ever launched into space. The Golden Record. Inside are sounds, music, greetings in dozens of languages, photographs of Earth, and small pieces of human civilization preserved on a fragile golden disc. It contains laughter, heartbeats, birdsong, waves crashing onto beaches, and voices from a planet that one day may no longer exist. Most likely, no one will ever play it. The chances of another intelligent civilization finding Voyager are extraordinarily small. The galaxy is simply too vast. Yet that was never the point. The Golden Record wasn't created because success was guaranteed. It was created because hope is one of humanity's defining characteristics. For thousands of years, we crossed oceans without knowing what waited beyond the horizon. We climbed mountains simply because they were there. We built telescopes to see farther than our eyes ever could. And eventually, we built a spacecraft that carried a message into the darkness, knowing that we would probably never receive an answer. That single decision says something extraordinary about our species. We are explorers, not because exploration is easy, but because curiosity refuses to let us stand still. Throughout this documentary, we've asked how long a real starship could survive in deep space. The answer turned out to be far greater than anyone might expect. It could survive longer than civilizations, longer than countries, longer than planets, longer than stars, perhaps even longer than galaxies as we know them. But the greatest discovery wasn't measured in years. It was measured in perspective. The farther we traveled into the future, the smaller humanity seemed. And strangely, the more meaningful our existence became. Against a universe nearly 14 billion years old, every human life lasts only an instant. Our civilizations appear and disappear in the blink of cosmic time. Our greatest achievements are tiny compared to galaxies. And yet, within that brief moment, one small species on one ordinary planet learned enough about the universe to send a machine beyond the edge of its own solar system. We looked into the darkness, and instead of turning away, we kept going. Maybe that has always been the real story. Not whether a starship can survive forever. Not whether humanity will reach another star. But that, for one extraordinary moment in the history of the cosmos, the universe became aware of itself through us. We asked questions. We searched for answers. We built machines capable of carrying those questions farther than we could ever travel ourselves. And somewhere right now, in the silent darkness between the stars, one of those machines is still moving, still carrying the echoes of a civilization that dared to wonder what lay beyond the horizon. Perhaps one day Voyager will be gone. Perhaps every spacecraft humanity ever builds will eventually disappear. But the curiosity that launched them, that may be the one thing capable of outlasting even the longest journey. Because in the end, a real starship was never just a machine. It was proof that a tiny civilization on a small blue planet refused to let the vastness of the universe stop it from reaching into the unknown. And maybe that is the greatest journey humanity will ever make.